warm welcome to all of you in this lecture on joining of polymer matrix composites. As you are well aware that this is the module number 7 of our course on processing of non-metals. We have seen the processing techniques for a large variety of non-metals, and now our focus is towards the secondary processing of non-metals. Whereas our focus primarily is on the composite materials, and within composites within the composites family our focus is primarily on the polymer matrix composites. In module number 7 we have seen that what is the need of secondary processing and why secondary processing is required. Just to revise and to make a brief background of what we are going to discuss today, secondary processing of materials is required in order to ascertain their structural integrity into big products or huge structural products. So, if we have to suppose make a building, in the building we cannot make the whole building in a single process. We will make so many different components separately using some of the techniques, and finally all these parts would be assembled together. They can be assembled by permanent joining processes, they can be assembled by temporary joining processes. So, a large number of parts would be joined together to make the complete structure. Another example, suppose we want to make an automobile. In an automobile, different parts are made up of different materials. Some parts are made up of plastics, another parts are made up of metals, another parts may be made up of some of the alloys of the metals, and when we have all these different parts, we have to combine these parts together to get the whole automobile. So, for joining or for assembling the total automobile, we require a large variety of operations, and these operations fall under the category of joining operations, or in another terms we can call them as the assembly operations. So, assembly operations and drilling and machining, all these fall under the secondary operations. So, in order to ascertain the assembly operations, sometimes we have to perform the machining operations, specifically in terms of drilling. Suppose I want to join these two parts together, one of the important types can be applying an adhesive and then making a joint, but in certain cases applying the adhesive may not be a suitable alternative. Then I need to make a hole inside the two plates and then use a mechanical fastening mechanism to make a joint. So, joints are basically required to ascertain the structural integrity of huge products such as buildings and automobiles, or even marine ships and aeroplanes. So, these are some of the examples where assembly operations are required and where different parts manufactured independently are assembled together to get the final product. So, as the title of today's lecture goes, joining of polymer matrix composites. So, there are two important terms in this particular title, that is joining and polymer matrix composites. So, joining is a very well developed technology in which there are so many different techniques used for joining, such as welding, brazing, soldering, and then there are certain mechanical fastening techniques which are used for joining the various structural members into a big structure. So, joining is a well developed technique. Polymer matrix composites we have already studied in one of our modules, that what are polymeric matrix composites, what is the matrix, what is a reinforcement, and why the matrix and the reinforcement are combined together to make a composite, and how these composites are better as compared to the conventional engineering materials, what are the application areas of the polymer matrix composites, and also we have seen at least 8 to 10 different techniques of processing of polymer matrix composites. So, the title has been explained with this discussion that we are going to focus on the joining aspects of a different class of materials, that is polymer matrix composites, that what are the important issues and challenges that we encounter when we go for joining of polymer matrix composites. We have seen that polymer matrix composites can be made in a different shapes, made in different sizes. So, whatever techniques we have identified, whatever techniques we have studied in our previous lectures on polymer matrix composite, we have seen that all the techniques give us a composite product, but this composite product now has to be assembled with certain other materials or with another composite in order to get a complete structure. So therefore joining of polymer matrix composites is very important. So we are going to focus on the issues and challenges which are there in context of joining of polymer matrix composites. Also we are going to discuss another technique, that is microwave joining of polymer matrix composites, in our next lecture, that is lecture number 4 in this particular module of secondary operations for non-metals or specifically for composite materials. So today our focus would primarily be on understanding that what is adhesive joining, what are the, we can say, important or salient features of adhesive joining, what are the salient features in mechanical fastening, and then towards the end we would focus on that what are specific requirements when we are going to join two composite adherents using a adhesive. Similarly, we will see that what are the issues and challenges when we are going to join two composite adherents, or adherents mean the two composite members. So composite members means that these are the structural members made by a composite material. Which composite material? That is the polymer matrix composite material. So here our adherents would be polymer matrix composite material. They can be in the form of a laminate or they can be in any other shape, and these will be joined with another materials either using a adhesive or using a mechanical fastening. Now what is the necessity for polymer matrix composite joints? Joining of polymer matrix composite has led to a new dimension of concern among the researchers. Why? Because it is not that easy as compared to the conventional engineering materials. We have seen so much of furniture. If we take an example of a furniture, wood is being joined to wood and using some or the other kind of adhesive or some or the other kinds of mechanical joints, wood is combined together, different parts of wood or different shapes of wood are combined together to get the furniture. So the joining techniques are well developed if we are talking about conventional engineering materials such as wood, but if we talk about these advanced materials such as polymer matrix composite, the joining aspects need to be addressed properly, or certain issues have to be addressed before the two composite adherents be joined satisfactorily, making a good quality joint which can take the loads that is going to come during the application of this particular composite material. So joining of polymer matrix composites had led to a new dimension of concern among the researchers, means there are efforts worldwide to design and develop tools and techniques for the effective and efficient joining of polymer matrix composites. Next on your screen you can see, to ensure the effective utilization of the developed materials for the welfare of the society, material joining becomes an important and necessary domain, which again emphasizes the importance of joining. Suppose we have designed, we have invented a very good, or we can say a very applicable engineering material which has got lot of applications, it can be used in a large variety of applications. The new material has been developed. Its application depends upon how effectively it can be joined with other members so that it can be converted into a structure or into a particular application. Independently, yes, there can be some applications, but many applications would be requiring this particular material to be joined effectively to other materials. So this particular slide is just emphasizing on the role of joining of advanced materials, that if we are able to join the advanced materials properly, then the application spectrum of these materials can be increased manifold. Now necessity of polymer matrix composite joint development. The joint is a source of stress concentration, everybody knows that. Improper design may lead to increase in stress concentration and may become a cause of failure during the service life of the product. So joint is an important, we can say, part of the total structure, and most of the structures may fail at the joint. Otherwise also the structures may fail in the member itself. If there is a huge structural member, the failure may take place in the bulk of the member also, or in the material of the member also, but it has been found that the joints act as one of the weakest links between the complete structure or in a complete structure. So joint design and a effective joining technique is a very important prerequisite to ascertain the long life or the failure free life or the damage free life of a structure. So joints and processing time and labor cost to the product. So joining and processing time, joining adds processing time and labor cost to the product. So certain times we would like to avoid the joining operations totally by making a near net shaped product. Suppose I need a particular product for a particular application, my focus would be to make it as it is without dividing it into 4 or 5 different components which later needs to be assembled. So the focus would be primarily to make a simple product which requires no assembly operations. Why? Because joints add processing time and labor cost to the product. So one approach can be that why not to totally avoid the joining process, which is not feasible or possible in most of the engineering applications. So these two slides have given us an idea that joining of advanced materials is very important, and we need to take proper care when we are going to join the two structural members together, and today's focus is that the structural members are made up of composite materials, that are polymer matrix composites. Now, what are the various applications of PMC joints? We have seen that joints are important, joining of PMCs is very important. There are certain important aspects which are specifically related to the joining techniques for polymer matrix composite that we are going to see in the subsequent slides. But what are the applications where these joints are used? The joints of PMCs are required for structural applications, which I have already told, that if I have made 2 or 3 different composite parts or polymer matrix composite parts, and then these need to be assembled into the structural or into a particular structural application, then the assembly would be required, and therefore the joints would be required. Point number 2 on your screen, joints ensure the assembly of the PMCs to the materials like wood, plastics, ceramics, metals to make a usable product, which I have already emphasized that if I develop a new material, I need to develop effective joining techniques for that material, that how effectively it can be joined with other class of materials such as wood or plastics. So that is another application of joints where the composite material is being joined with other materials such as woods and plastic. Why? Because when I have to make a complete product, it may be made up of 5 different materials, out of which one is a polymer matrix composite, another 4 may be a metal, a alloy, a plastic and wood. So I should have effective joining techniques so that this composite can be joined with other engineering materials. That is another application area where the joints are very important. Next point, the joints may have to serve other purposes. Sometimes the joints are made in such a way that they serve a lot of purpose, such as in structural applications such as vibration damper. So they can be used as vibration damper, they can absorb the vibrations, they can be used as sealants, thermal conductor of or insulator, electrical conductor or insulator. Sometimes the joints are designed in such a way that they act as or they serves the following purposes which are there on the screen, that they can act as vibration damper, they can act as electrical or thermal insulator or conductor. So joints are very important, therefore we need to understand the importance of joining. On your screen you can see the two mostly used joining techniques or types of joining methods. So first one is the adhesive joint, which is a permanent joint, means the two composite adherents, when they have been joined together, they cannot be disassembled without breaking the joint. So adhesive joint is a permanent joint. On your screen you can see this is one adherent, this is another adherent, and this yellow portion is the adhesive which has been applied. This is a lap joint. The yellow adhesive has been used to join the two composite adherents together. Then we can have another type of joining method, that is mechanical joint. In mechanical joint on your screen you can see this is a mechanical fastener which has been used to join two composite adherents. Now these grey raw materials or adherents are made up of composite material. They can be made up of any other engineering material because this is a very general joining technique which can be used for all different types of materials. This is just to highlight that what are the different types of joining method, because these joining methods are also used for the polymer matrix composites. Now these are types of adhesive joints, just for your reference, that how the composites can be joined using which type of joint configuration or joint geometries. On your screen you can see you can have a single lap joint, you can have a butt joint, you can have a single strap butt joint, a double strap butt joint, double lap joint or tapered double strap. So there can be a huge or a large variety of joint configurations that can be used to join the composite adherents together. You need to have the raw material which is a composite material. So we have a composite laminate or a composite plate, and that composite plate can be joined to another composite plate or another wooden plate or another metallic plate using any of these type of joint configurations by applying the adhesive, and then these two structural members can be joined together. But there are few issues involved that we would be seeing in the subsequent slide. So these are certain, or we can say, important type of joint configurations or joint types which are used for joining the composite adherents. Then we have the types of mechanical joints. We can have again a single lap joint, which is shown here, a double lap joint, on your screen you can see, and then a butt joint is also there. So we can make different types of joints in case of mechanical joints also. Now what are the differences between the adhesive joints and mechanical joints? We have seen that what is adhesive joint, where we apply a adhesive between the two plates that we want to join together. In case of mechanical fastening, we use a fastener to fasten the two composite plates together or the two structural members together. Now what are the differences? Because each one of these has got certain specific application areas. So on your screen you can see, in adhesively bonded joint, the load is distributed over an area rather than being concentrated at a point. For example, in mechanical fastening, the load can be concentrated at the point where the fastener is fastening the two composite plates together, whereas in adhesively bonded, there is a bond area where the adhesive has been applied. So the stress distribution is quite uniform. So once again, I am reading what's there on the screen. In adhesively bonded joint, the load is distributed over an area, that is the bond area where the adhesive has been applied and where the two plates have been joined together, rather than being concentrated at a point as in the case of mechanical fastening. This results in more uniform distribution of stresses. So adhesive joints in such type of cases may provide to be a better alternative as compared to, or may prove to be a better alternative as compared to a mechanical fastening. Adhesively bonded joints are more resistant to flexural, fatigue and vibrational stresses than mechanical joints because of uniform stress distribution. So therefore we can see that if we have a uniform stress distribution, the joints are more resistant to flexural, fatigue and vibrational stresses. So adhesively bonded joints can be said to be more, we can say, effective when more uniform stress distribution is desired. The weight increase is negligible with adhesive bonding as compared to the mechanical joint. Suppose we want to join at 10 different places and we require 10 different mechanical fasteners. So these 10 different mechanical fasteners would certainly add to the weight of the structure, whereas if we have to join two plates together, we can apply the adhesive and join the two plates, and the weight addition, as we can see on your screen, point number 1, the weight increase in case of adhesively bonded joints is lesser as compared to the mechanically fastened joints. Point next, adhesive not only bonds the two surfaces but also seals the joint. The seal prevent galvanic corrosion between the dissimilar adherent materials. So we can have another advantage of adhesive joints, that it not only forms the joint between the two plates or two composite adherents, but it also seals the joint. So there is chances of leakage are also minimized. Moreover, it prevents galvanic corrosion also when we are combining or when we are joining a composite plate with a non-composite plate or a metallic plate or any other plate in which the corrosion may take place. So galvanic corrosion is minimized when we are going to use a adhesively bonded joint as compared to a mechanically fastened joint. Adhesive bonding provides smooth surfaces and generates no change in part dimension. That is another advantage. Now suppose I have a uniform profile of the final component. I do not want anything protruding out of the profile. In that case, if I have to join that profile with another profile, I would not like to have a mechanical head of the bolt coming out. Therefore, if I join it using a adhesive, I will be able to provide a smooth surface to the joint as well as to the structure. So if we do not want anything protruding out of the, we can say, structure and we want a complete smooth profile without anything on top of the surface, we would definitely go for adhesively bonded joint. Adhesive bonding is often less expensive and faster than mechanical joining. That can be true in some of the cases, but in some other cases the mechanical fastening may provide to be a quick solution as compared to adhesive bonding, specifically in those cases where the adhesive that we are using may be requiring long curing time, that we have already seen what do we mean by curing, or in simple terminology, get set ready means after applying the adhesive, the time required for the complete, we can say, completion of the joining process, where the polymer or the chemical that we have used as the adhesive has completely formed the joint. So if the curing time is very large, then the adhesive joining may also take lot of time, but in most of the cases we can say adhesive joining is often less expensive and faster than mechanical joining. Mechanical joining allows repeated assembly and disassembly for repair and maintenance. Now we come to the advantage of the mechanical joining. Till now we have seen that adhesives are, or adhesive joining is better as compared to the mechanical joining, but here we see that when we have to have a regular maintenance of the structure which has been joined together using mechanical joining, we can disassemble the structure and removing the mechanical fastener, opening the structure, doing the maintenance and then again closing. So mechanical joining allows repeated assembly and disassembly for repair and maintenance, whereas if you have joined the same structure using a adhesive, you need to break the joint and then only you can do the repair and maintenance. So disassembly is not possible with the adhesive joints, whereas disassembly is possible with the mechanically fastened joints. Mechanical joints offer easy inspection and quality control, which is very obvious as compared to the previous point which we have already highlighted. Mechanical joints require little or no surface preparation as compared to the adhesive joint. So therefore adhesive joints require we can say surface preparation before the adhesive can be applied in order to get a good bond strength. If we do not do the surface preparation, the bond strength that we would get would not be of very high quality. Now what are the factors that influence the failure of adhesively bonded joints? Now these particular factors are particularly relevant in case of polymer matrix composites. So on your screen you can see there are large number of factors, even there can be more number of factors than what are listed on this particular slide, which affect the failure of the adhesively bonded joint. Now we have already seen that what are the advantages of adhesive joints, we have seen what are the advantages of mechanically fastened joint. So when we have those advantages and we are using the adhesive for joining purposes, there are bound to be certain important factors which we should keep in mind in order to avoid the premature failure of the adhesively bonded structures. So what are the important points, salient features that should be kept in mind while we are designing a particular joint which has to be adhesively bonded? First and foremost is the type of adhesive. There is a huge variety of adhesives which are available, so we have to properly choose that which type of adhesive would be able to provide us a good quality joint. Next one is the mechanical properties of the adhesive. Now each adhesive will have certain properties and these properties will dictate the failure of this particular joint when it will be subjected to different types of loading conditions. So mechanical properties of the adhesive also needs to be studied. Apart from the mechanical property, there has to be other properties like the physical and the chemical properties, as well as the important points such as the toxicity and the other chemical inertness and other aspects which needs to be studied when we are going to use, and these particular things would help us to make a joint which is good quality, efficient, effective, and usually leads the complete designed life of the structure. So we have seen type of adhesive, mechanical properties of the adhesive, then comes the mechanical properties of the adherent or the structural members which we are joining using the adhesive. So these structural members are composites in our today's lecture, and there is a big problem of delamination in the composites. So sometimes the adhesive may not fail, even the bond between the adhesive and the adherent may not fail, but the adherent itself may fail. So that is another problem. So we have to see that what are the mechanical properties of the adherent, so that it should be able to provide us a good designed life of the joint. So the adherent should also not fail. So mechanical properties of the adherents also should be taken into account. Then the bonding between the adhesive and the adherent also is very important. In certain cases it has been seen that the adhesive which has been used with a specific set of adherents does not bond with the adherent properly, and that leads to the failure of the bonding. The adhesive does not fail, the adherent does not fail, but the bonding between the adhesive and the adherent fails, and under a typical type of loading, this particular structure is not able to take a load, or this particular assembly of two adherents is not able to take the load. Another important point, that is the wettability of the adhesive. The adhesive should be able to wet the two adherents properly and form a very good joint. So wettability is also to be taken into account. Another important point is the surface properties of the joint surface. So surface preparation is required, otherwise the joint may fail, or the bond strength that we get without the surface preparation of the adherents would not be as good as desired. Then the type of loading is also very important. That this we will try to understand with the help of a diagram, but prior to that we need to understand that what is the type of loading. Type of loading, suppose we have a joint, we can have a tensile loading, we can have a compressive loading, we can have a bending load that is coming on that particular joint. So our joint should be able to sustain these type of loading. So the point to highlight here is that there are so many factors which needs to be taken care of when we are using the adhesive joining process to join the two composite adherents together. So on your screen, whatever we have discussed, I will just once again revise. This is the adherent, composite adherent. It can be made up of glass fiber reinforced plastic or carbon fiber reinforced plastic. Another adherent which can be of the same material like glass fiber reinforced plastic or carbon fiber reinforced plastic, or can be any other material also, type of material also. So we have two adherents, these grey members are the adherents and the yellow portion is the adhesive, as is very clearly highlighted here with the help of an arrow. Yellow portion is the adhesive, and these red lines indicate the interface between the adhesive and the adherent. This is the adherent, this is another adherent, and this red lines indicate the interface, very thin interface between the adherent and the yellow adhesive. So this is the simple joint which has been made by the adhesive bonding. So in this particular case the failure may take place because of the type of loading. Here one type of loading is shown, there can be different types of loading that may come on this joint, and that would dictate the failure of this particular joint, that the failure mechanism or the failure initiation and propagation in this particular joint. So the type of loading, the mechanical properties of the adherents, these are the two adherents, the mechanical properties of the adhesive, the bonding between the adherent and the adhesive, these are some of the important points. And when we apply the adhesive, we need to prepare the surface here and here, so that a proper bonding may develop between the adhesive and the adherent. So if that bonding does not develop, then there is every chance that this particular assembly of two adherents may fail under different types of loading conditions. Now factors influencing the failure of the mechanical joints. Now adhesive joints we have seen, in case of mechanical joints different types of failure may take place. So we have different types of loading similar to that in case of adhesive bonding. Stress concentration, because we are making a hole inside the two joints, that inside the two members which we are going to join. So when a hole is there or any other structural discontinuity is there which may act as a stress concentration site. So there are different types of notches which act as stress concentration site, but in our case when we are trying to join two structural members together, or in other terms or in simple terms two plates together, we want to join using a mechanical fastener, we need to make a hole in these two plates. and when a hole is made, it will act as a site of stress concentration. That is another issue which may later on act as a failure site for the joint when the joint is loaded under different types of loading conditions. Next point, the method of hole making. In case of composite adherents, if you remember in lecture number 1 and lecture number 2, we have seen that hole making is one of the most important, and we can say one of the paramount important practices in case of composite materials. It is a very important task. Why? Because it leads to a lot of damage around the drilled holes. So when we are using two composite plates or two composite laminates that we want to join together in order to make a assembly, if we require to make a hole, the hole will definitely induce certain damage or it will generate certain damage around the drilled hole. So which technique has been used for making the hole will also dictate the failure that would take place later on when this joint would be loaded under different loading conditions. Next point, drilling induced damage, which is directly related to point number 3, that is method of hole making. If the drilling induced damage in terms of delamination or fiber pull out or matrix burning takes place, this particular damage is certainly going to affect the behavior of this particular joint which has been made by mechanical fastening. So in case of composite adherents, because this damage takes place, the joints are not, we can say, very effective and efficient. So the need of the R, or we can say one of the important points to be taken care of when we want to join two composite adherents together using the mechanical fastening technique is to minimize the drilling induced damage. So when these two parts have to be joined together, when we have to make a hole in the two composite laminates, due care should be taken to avoid the drilling induced damage, because if the damage takes place, this particular damage is going to affect the behavior of this mechanically fastened joint of composite plates at a later stage. Then the mechanical properties of the fasteners are also equally important. Sometimes we have seen the composite adherents can even provide us the strength which is better than metals. So sometimes these fasteners are made up of metals only. So the mechanical properties of the fasteners is also very important. It may so happen that the composite adherents, when they have been joined together with a mechanical fastener, and the fastener is made up of a metal and it is loaded, the adherents are able to take that load, but the failure of the fastener takes place. Why? Because it did not have the requisite strength to take that load, or did not have the requisite, we can say, power to take that kind of a loading. So mechanical properties of the fasteners is also equally important in order to provide a very, we can say, durable life of the joint which has been made by the mechanical fastening technique. Now on your screen, what we have already discussed, these are two composite adherents, adherent number 1, adherent number 2, and the loading has been applied. In between we have a mechanical fastener, and we can see this is zigzag type of a delaminated area. Why this delamination in the adherents has taken place? Because of the hole making operation, which we have already seen in lecture number 1 and lecture number 2, that whenever we try to make a hole inside a composite laminate, there is bound to be certain damage that is all around the drilled hole. So this red portion shows the damage which has taken place around the hole. This particular hole and this particular hole which has been made in the composite adherents with the drilling operation. So when this will be loaded, the fastener may not fail, but the adherents may fail because of this induced damage which has already present before the actual fastening process. So there are certain specific issues related to the adhesive joining and mechanical fastening of the composite adherents. Now we will try to briefly highlight that what are these important issues. Now these are issues and challenges in adhesive bonding and mechanical fastening or bolting. A thin coating may be applied prior to joining that completely changes the chemistry of the part surface. So we want to do the surface preparation of the composite adherents before the actual joining process in order to get a very good bond strength. The physical and chemical characteristics of the bond surface have a significant effect on the bond strength. So the summary of this particular point is that if we want to get a good bond strength, we need to do the surface preparation of the two surfaces on which we are going to apply the adhesive in order to form the adhesively bonded composite joint. Point number 2, an adhesive must be able to fully wet the substrate surface. This occurs when the adhesive is lower in surface energy than the substrate or the adherent. So the summary of point number 2 is that the wettability of the adhesive should be good and it should be able to wet the total bond area in order to form a very good quality adhesive joint. Heat and pressure may be required during the bonding operation. This may limit the part size if the curing in an oven or autoclave is required. So sometimes we may be requiring to put heat and pressure while we are doing the adhesive bonding, and if this heat and pressure has to be applied in the autoclave, which we have already seen as one of the techniques in one of our previous lectures. So if within a autoclave we have to make this joint by applying pressure and heat, then the total size of the part is limited by the size of the autoclave, because we cannot put a very big size component or a assembly in the autoclave. So that is another important issue that is associated. With some adhesives, a long curing time may be required. As I have already highlighted in today's lecture, that adhesive bonds have a certain advantage because they are quick and cheaper as compared to the mechanical fastening, but if the curing time of the adhesive is long, then the adhesive bonded joints may be taking a huge amount or maybe a large amount of time before the final joint is ready. So long curing time sometimes is an issue with the adhesive bonding joints. Adhesive bonding requires more training and rigid process control than the mechanical joint. So the technique and the, we can say, requirements of adhesive bonding are, we can say, more skillful as compared to the mechanical fastening process. So now we will see the summary of disadvantages of adhesive joints and the disadvantages of the mechanically fastened joints. Why? Because our next lecture is on microwave joining of polymer matrix composites, in which we will see that what are the disadvantages of adhesively bonded joints and mechanically fastened joint which are overcome by the microwave processing techniques. So this is just a summary of what we have already covered in today's lecture, that is, what are the adhesive joints, what are the mechanical joints, and what are the specific requirements in case of composites when we are talking about the mechanical fastening of polymer composites and the adhesive joining of polymer composites. So we will just now summarize the disadvantages of both the techniques. First important disadvantage is adhesive bonding usually requires extensive surface preparation before bonding. The area where the adhesive has to be applied needs to be prepared before the actual adhesive bonding to take place. Next point, pressure may be required during the bonding operation, as we have seen that autoclave may be required in certain instances. With some adhesive, a long cure time may be needed, and thus the total process of adhesive joining may take a long time. Health and safety could be an issue. Why? Because the adhesives are chemical substances and sometimes they may react with the composites, because composite also has a polymer matrix which is also a chemical. So when these two chemicals are coming in contact and we are supplying heat, in some cases there may be certain reaction and certain fumes may be generated which have to be avoided. So before using a particular type of adhesive with a particular type of a composite adherent, due care should be taken in order to avoid these health and safety issues. Inspection of a bonded joint is difficult, which we have already seen that the adhesive joining forms a permanent joint which is not easily possible to disassemble. So if we want to do an inspection within the joint, it is sometimes not possible. Another important point, surface treatments used for adhesive bonding are generally hard to control in an industrial environment and affect directly the strength and durability of bonded joints. So another important point to note is that the surface preparation is a tedious task, and if it is not done properly, there is every chance that we may not get a very good bonded joint. So surface treatment is difficult to control in many cases. Now what are the disadvantages of mechanical joints? One of the most important disadvantages is stress concentration created by the presence of holes and cutouts, which is worsened by the lack of plasticity, limiting stress redistribution. So, summary of this particular point is that stress concentration definitely takes place around the holes and the other types of cutouts, which needs to be avoided, but which is unavoidable when we have to do the mechanical fastening. Why? Because when we want to use the mechanical fasteners, we need to have holes in the composite adherent. So, this stress concentration is an issue. Point number 2, delamination originating during the drilling of composite laminates, which we have already seen. Specifically in case of laminated composites or specifically in case of polymer matrix composites, delamination is a big issue. When we make a hole, the plies or the layers or the laminate tends to delaminate, and when the drill pierces through or it goes through the laminate, delamination takes place, and this delamination acts as a failure initiation site when this particular component is subjected to different types of loading. Now, suppose I have one component or one plate, on top of it I have another plate. So, these two plates have to be joined together with mechanical fastening, and I make a hole in these two plates. I make a hole in this plate and I make a hole in this plate and put these two plates together and use a mechanical fastener. If these two plates are made up of a composite adherent or a laminated composite, there is bound to be delamination which may take place, and when I am using a mechanical fastener to bound these two plates together or to assemble these two plates together and then loading this assembly, this particular delamination which has taken place because of the drilling action on the laminates will certainly affect the performance of the assembly. So, that is another issue, the delamination that take place in the composite adherents. Next point, differential thermal expansion of fasteners relative to the polymer composites. So, the two materials are different. Fasteners are usually made up of metals and the composite are usually made up of the fibers and the polymers. So, the thermal expansion is bound to be different. So, if the joint is being used under elevated temperature, thermal expansion may be different and may act as a cause of failure. Mechanical joints add weight to the structure and minimize the weight saving potential of the composite structure. As we have seen in our previous lectures that the use of composites is advocated in specific circumstances where weight saving is one of the prime design criteria. So, composite structures are used where we want to save a lot of weight, but when we are using mechanical fasteners, the weight of the fasteners would add to the weight of the structure. So, therefore, the basic criteria of weight saving which we can get with the composite structure sometimes is compromised in case of the mechanical fasteners, because mechanical fasteners then reduce the weight saving potential of the composite structures. The fasteners create potential of galvanic corrosion because of the presence of dissimilar materials, because fastener, as I have already seen, would be of a different material as compared to the adherents, because adherents in our case are composite adherents. So, when composites are in contact with any other material, the chances of the galvanic corrosion are aggravated. So, that is another disadvantage of the mechanical joints. Finally, they create fiber discontinuity at the location where a hole is drilled and expose fibers to chemicals and other damaging environment. Again, this is related to the drilling induced damage of composite laminates or composite adherents. When the damage takes place at the hole wall, there are micro voids or there are small cracks that are developed, and when this joint suppose is subjected to a damaging environment, there are chances that the moisture may go into these cracks and may cause a failure site, and then there are other chances that some chemicals may peek into or seep into these micro channels which have been generated because of the damage around the drilled holes and may certainly affect the in-service performance of the mechanically fastened joint. So, there are certain issues related to the adhesive bonding of polymer matrix composites and the mechanical fastening of the polymer matrix composites which have to be looked into in order to provide a good service life of the joints. So, to summarize what we have covered in today's lecture, we have seen what is mechanical fastening, what is adhesive bonding. We have seen what are the issues and challenges related to mechanical fastening and adhesive bonding, specifically in case of polymer matrix composites. We have tried to understand with the help of diagrams that how interfacial debonding may take place, or what are the important factors which may lead to failure of a adhesive joint in case of polymer matrix composites. We have also seen that what are the factors which may lead to a failure of a mechanically fastened joint, specifically in case of polymer matrix composites. And finally, we have seen that what are the disadvantages of the adhesively bonded joints and the mechanically fastened joint, so that we can lay a foundation of discussing the microwave joining of polymer matrix composites. So in our next lecture in module 7, we would focus on the microwave joining of polymer matrix composites. Thank you.